Hello, everyone. Today we are going to start to learn about something called conditional probability, which is probability assuming that an event has already happened. We're going to start by looking at some tree diagrams, and then in our next video, we'll look at two-way tables. All right, so to start off, conditional probability is the probability of an event happening assuming another event already occurred. So, for example, if we have two events, A and B, the probability of A given B is an example of conditional probability. So this vertical line here means given when we're talking about probabilities, the probability of A given B. And what this means is assuming B occurred, what is the probability of A? And this first part, B occurring, is important because if B occurs, it could have an effect on the probability of A. It could change the probability of A happening. So first we'll go through a quick example. So we have a company that makes baseball hats for New York Yankee fans. Their machine sometimes malfunctions 5% of the time and forgets to put a brim on the hat. So we have a Yankee with no brim. They have a quality control machine that checks the hats and removes any hats that it identifies as having no brim and puts them in a separate reject pile. And 90% of the time, it's able to accurately identify that this hat has no brim. We're trying to answer the question, if a worker randomly selects a hat from that reject pile, what's the probability that it is an actual defective hat? It actually has no brim. For this problem, we're going to create a tree diagram to help us answer this question. Here, the question being asked actually has two events. We could call event A the event that the hat is defective. In other words, the event that we have a no brim hat. And B is the event that the hat is separated into the reject pile. So assuming that the hat is in that reject pile, what is the probability that it is a defective hat? In other words, here we're trying to answer the question, the probability of A, that the hat is defective given that B has already occurred. So we'll start off with a tree diagram. So first we have our big pile of hats, all of our hats, and our hats are either defective or correct. So they either have no brim hat, or it has a brim. And we know that 5% of the time, we have no brim. 95% of the time, it does in fact have a brim. Next, we're looking at the quality control stage. So for this stage, we're looking at, let's assume that it has no brim at that point. So we're going down one of the branches of this tree. If it has no brim, then 90% of the time, the machine correctly identifies it and puts it in the reject pile. 10% of the time, the machine misses it and it goes on to sell. So it goes on the sale floor. Assuming the hat has a brim, again, 90% of the time it identifies and it goes ahead to sell that hat. 10% of the time, though, it incorrectly identifies, so it's only accurate 90% of the time, and it places the hat in the reject pile. So we're looking at what's the probability that, given it's in the reject pile, it has no brim. So here what we could do is look at our two events that end up with the reject pile. And we could calculate what percentage of the hats overall end up in that pile. And we can do this by multiplying our events. So we could take our 5%, multiply it by 90% to find what percentage of all of the hats end up in the reject pile, given that it has no brim. And we can also use numbers to help us out too. We could assume, for example, let's say we make 10,000 hats. Then if we have 10,000 hats, 5% of that have no brim, 95% of that have a brim. So this looks like 500 hats have no brim, 9,500 have a brim. And then of that 500, 90% are correctly identified and rejected. So 450 hats. If we multiply these percentages, 5% and 90%, then we can see that we end up with 4.5% of the total hats, which is the same as 450 out of 10,000. We could go down our bottom tree. So 95% probability that it has a brim, and then 10% probability it ends up in the reject pile. We could start with our numbers, 9,500 times 10%. That's 950 hats. If we multiply the percentages, then we have 95 times 10%, which gives us 9.5% of all hats. So we can use numbers to help us out. We could also just write down the percentages. So all in all, we have, let's scroll down a bit, 450 hats. That were in the reject pile that have no brim, and 950 hats that have a brim. Or we could look at percentages, 4.5% have no brim, whereas 9.5% have a brim. So to find the probability that given it's in the reject pile, it has no brim, we could look at the number of hats that end up with no brim and divide that by the number of hats that are in that reject pile. So here, for example, we have 450 plus 950. It looks like 1,400 or 1,400 hats ended up in that reject pile. And out of those 1,400 hats, 450 of them have no brim. Out of 1,400 total. So out of all the hats in the reject pile, 450 of them have no brim, which we could divide and come up with a percentage. We end up with about 32.14% of the hats in the reject pile have no brim. We could also use percentages. We could add our percentages up, end up with 14%, and then take our 4.5% and divide it by 14%. And we'll end up with that same number. So what this means is that in that reject pile, only 32%, or a little bit less than 1/3 of the hats, are actually defective. So even though our machine is accurate 90% of the time, the issue here is because so many of the hats have a brim, 95% of them have a brim, even though only 10% of them are going to be incorrectly thrown in that reject pile, that 10% ends up being a lot more. So we can see here 950, a lot more than the 90% of the accurately identifying no brim hats. So this is an example of how we can use a tree diagram to answer questions about conditional probability. As you can see, to find these final numbers, we multiplied our percentages or numbers down the tree.